Welcome back to Physics 152 Online. We're starting a new section, and the important phenomenon that will dominate the topics in this section is called electromagnetic induction. And so we'll begin reviewing magnetic flux and then go on to talk about Faraday's law and induced electromagnetic force. Earlier, we mentioned that Gauss's law for magnetism tells us that the magnetic flux through any closed surface is zero. But sometimes we want to calculate magnetic flux through surfaces that aren't closed. And so this is just a reminder that the definition of magnetic flux, similar to the way we defined electric flux, is the integral over a surface of B dot dA, and that is phi sub B. Now here's a pictorial example just reminding us how you would set a calculation like this up. You have some sort of surface and there's a magnetic field that is passing through that surface. The normal vector n hat is in the direction of the dA vector that points normal to the surface at a particular point, and so the dot product would involve the angle between those two vectors. Remember that this quantity flux, even though it's a little bit difficult to grasp, it comes from the Latin word for flow. And in this case, even though the magnetic field lines don't really represent things that are moving, they do tell us a direction. And the flux is a quantitative measure of the number of field lines that pass through a particular surface. And here's an example. If we have a bar magnet and if there's some sort of surface distance away from one of its poles, the field lines come out of the North Pole, and we can see here that there will be a net flux passing through such a surface. Now, historically, here's what happened in 1819 and 1820. That's when Ørsted, and then later followed by Ampere and Biot and Savart, developed the relationship between electric current and magnetic field. And basically the idea was that an electric current produces a magnetic field, and Ørsted was the one who discovered this through the deflection of a compass needle. So shortly after this time, in the early 1830s, Michael Faraday, who was not a skilled mathematical scientist but was a very talented experimental scientist, decided that he would test to see that if electric current can be used to produce a magnetic field, maybe I can find a way to use a magnetic field to produce an electric current. And so Faraday historically set up an experiment that looked something like this. He had an iron ring, sometimes this is called the iron ring experiment, and on one side of the ring he had loops of wire passing around the ring connected to a battery, and that eventually he would close the switch in this battery. And on the right side of the ring he wrapped a second coil, and you'll note that these two coils, the primary and the secondary coils of wire, are not electrically connected, although they're both wrapped around the same iron ring. And then he connected this to a galvanometer, or we would just probably say a voltmeter today, and his thought was maybe when I pass current through the primary circuit on the left using the battery, the magnetic field that's produced inside those loops of wire, and that the iron, since iron is ferromagnetic, it conducts magnetic field over to the secondary loop, that maybe the magnetic field that I'm producing in the secondary loop or the secondary coil will produce a current. And so Faraday tried the experiment and he failed, because when he closed the switch there was no current that was generated in the secondary loop, except what Faraday noticed was in the instant just after he closed the switch, there was a very slight deflection in the needle on the galvanometer, and then it returned to zero. So it indicated that something was happening in the secondary coil. There was a very small current, but it lasted just a very short time. What Faraday also noticed, somewhat counterintuitively, was once the switch was closed, if he opened the switch again, he saw another deflection in the needle on the galvanometer, except in the opposite direction. So even though we have to say, strictly speaking, that Faraday failed in his idea, he did discover the fundamental principle that a changing magnetic field can be used to produce a current, because this experiment showed that when you close the switch, or for that matter, if it's already closed, when you open the switch, the field passing through the secondary coils would change, and that changing magnetic field, while it was changing, led to a deflection in the galvanometer needle. And we would say more fundamentally that the changing magnetic flux that was caused because of the starting or stopping of current and the magnetic field that was produced in the secondary coils, that changing magnetic flux caused there to be an electric field, and that electric field caused the charges to move in the wires of the secondary circuit. So here is a little demonstration, and I'll do something like this in class, that's similar to Faraday's experiment. If we have a solenoid with many turns of wire connected to a galvanometer, and then we take a bar magnet and thrust it into the opening in the solenoid, we'll see a deflection in that needle. And then conversely, if you pull it out, if it's already in there and you rapidly pull it out, the changing magnetic flux through the solenoid coils will also cause a deflection in the galvanometer needle. And Faraday, what his enduring contribution was not only to notice this effect, but also to be able to quantify it. And what he noticed, because this the language that was used to talk about forces that cause charges to move, they called it an electromotive force, he found that this epsilon that was induced by the changing magnetic flux was equal to minus the time rate of change of magnetic flux. So it's not just the magnetic flux itself that produces the current here in the solenoid, but it's the changing magnetic flux. And the minus sign is an indication that if the flux is increasing, then the electromotive force acts in a sense to oppose that, and if the flux is decreasing, then there's similarly the induced EMF opposes the change in the flux that led to it being produced. So just to note Faraday's law, since the electromagnetic force has units of voltage, we can see that the unit volts must be equivalent to whatever's on the right hand side, and flux is a Tesla meter squared, so Tesla meter squared per second is equal to volts. Now here is an important question. I said just a minute ago that the magnetic flux that changes actually produces an electric field. And why did I say that? Well, the question that you might ask in looking at this kind of demonstration is, what produces the force that causes the charges in the circuit to move? All we're doing is putting a magnet in or pulling a magnet out. And importantly, it can't be the magnetic field. The magnetic field of the bar magnet can't cause charges to move, because we already know from our study of the motion of charges and the way that they are deflected by a magnetic field that all the magnetic field does is change the direction of their velocity. It doesn't increase or decrease their speed. So magnetic fields can't do work on charges. Magnetic fields alone cannot take a stationary charge and cause it to accelerate. So the only thing left that we know of that can act and produce a force on electric charge is an electric field. And so we conclude that there must be an electric field that's being set up in the loops of the coil that cause the charges to move. But it's not an ordinary electric field. And often we call this kind of a field a Faraday field, so that we remember that it differs significantly from an electrostatic field. Faraday fields are inherently dynamic because they are caused by the time rate of change of magnetic flux. And one thing that we can say that illustrates this difference is that the EMF that's induced around the circuit in which the magnetic flux is changing can be written as the integral of an electric field dotted into dl. But note that this integral is around the entire closed circuit, the entire conducting path that the charges go around. And if we were writing down an expression for the potential difference in a region where there was an electric field, we would write down that this was equal to minus the integral of E dot dl, and that would give us the voltage. But one of the properties of electrostatic fields is that if you go all the way around some kind of loop and you integrate E dot dl, you get zero, because going around a loop brings you back to the same place you started, and the voltage has to be, there has to be no change in voltage if you go all the way back to the same point in the loop. So Faraday's law tells us that this E, and I've labeled it NC to indicate that it's a non-conservative electric field, and it gives us a net EMF when we integrate all the way around the circuit. So that this field can keep the charges moving even all the way around the circuit, and that makes it different than electrostatic fields. And so we'll close today with a discussion of what's called Lenz's law. And Lenz's law is really just a convenient way for us to remember the polarity of the induced EMF that Faraday's law introduces. It'll tell us if we have some kind of a conducting loop and then there's a magnetic flux that's changing through that loop, it'll tell us what the direction of the current flow that's induced happens to be. And here's one way of stating the law. The induced EMF and the induced current that EMF produces are always in such a direction as to tend to oppose the change, and this is the change in the magnetic flux, that produced them. And that seems a little bit vague, but let's flesh it out by doing an example. So here imagine that we have a conducting wire loop, and there's no battery here, so initially there's nothing flowing in that loop. It's just a conducting loop. And we have a magnetic field indicated by the X's that's pointing into the page. And now imagine that we can control that magnetic field and make it increase. So there is a magnetic flux passing through this wire loop, and since the magnetic field is increasing, the flux is also increasing. Faraday's law then tells us that there will be an electric field that will be produced that will cause the charges in the wire to move, and it will produce a current. So our question is, what direction does the induced current flow in this situation? And we're saying again, the B field is pointing into the page, but it's increasing in magnitude. So here's how we use Lenz's law, which is the statement up here that tells us the induced EMF and current tend to oppose the change that produced them. Here's how you do it. Okay, we notice that the flux through the loop because of the magnetic field pointing into the page is increasing. Now we use Lenz's law, and what Lenz's law tells us is that whatever current is induced in this wire loop, it will have a magnetic field that opposes the original change in flux. And so think about that for a second. The flux caused by the magnetic field into the page is increasing. So in order to counteract that or to oppose that, the induced current that's in the loop must be out of the page, pointing out towards us, because originally the magnetic field into the page was increasing. So all we have to do now, noticing that the magnetic field that's caused by the induced current is pointing out of the board, we use our right-hand rule. We curl our fingers around in the direction of that current flow, and the thumb points in the direction of the magnetic field. And so the use of the right-hand rule tells us that the induced current must flow counterclockwise in order to be consistent with having an induced magnetic field out of the page. Now, notice that this will only happen, this current will only flow as long as the magnetic field keeps increasing. If the magnetic field stops, then the current will go away and there won't be any more induced field or current. So let's do another example. Here is a physical situation where the magnetic field isn't changing, we're not controlling it and making it get larger, but we're moving a magnet toward a conducting loop. And so then inside the loop, which is the surface that we will calculate the magnetic flux for, inside that loop, as the magnet approaches, the magnetic field does get stronger. And we're not going to actually calculate what that flux is. You can see with the field lines that that would actually be a pretty complicated thing to do, because the field across this surface inside the loop is not uniform. It's changing direction and it's changing magnitude as well. But all we need to do is ask, well, if this magnet's moving to the right with the north pole pointing toward the loop, which way would the induced current flow in the conducting loop? And notice, as the magnet approaches the loop, B, of course, points to the right, and it's increasing. So delta B is pointing to the right as well. It's getting larger. So, according to Lenz's law, the induced field that the induced current produces opposes this change, so the induced field would point to the left, and therefore, using the right-hand rule, the induced current would flow counterclockwise around this loop. And one thing to notice as a result of that, since this induced field this induced current points counterclockwise, the right-hand rule tells us, like we said above, that the induced B points to the left. And so the current loop that is produced by having the magnet approach it acts like a tiny magnet whose north pole is on the left-hand side. That's because the induced magnetic field points to the left. And so as this magnet on the left is approaching the loop on the right, there will be a repulsive force. And we'll see that that has physical consequences that we'll talk about a little bit later on. So, hope this has been a good introduction, and I will see you in class.